Good morning everyone. Here we want to start our fourth unit, that is the baseband receiver, in which we are supposed to study about the signal space representation. In that we are supposed to see geometric representation of signal. Then we will see about conversion of a continuous ABGN channel to vector channel. Here we will see maximum likelihood decoding. Then we see correlation receiver and probability of error. We will see one by one. So here we can start now from the baseband receiver, in which our first topic is we are supposed to see geometric representation of a signal. So when we are using the signal processing applications, at that time we have seen it will involve decision making at some stage. And if you see the electronic signal processing systems such as communication, radar, image processing, speech, that will require the detection of an event so that we can gather more information. So if we are taking one example for the detection, we can solve using the statistical theory, as there is a randomness involved in the same. So we can use the statistical theory to decide which event has occurred is known as a detection theory, or we can say that as a decision theory. So here if you see, you can observe here the diagram for the digital communication. Already in our first unit we have seen it will consist of transmitter, receiver and channel. So when we are supposed to see digital communication, at that time we are saying we will require their detection mechanism in case of the baseband signals. So if we are using any BPSK, BFSK, QPSK, at that time in the baseband receiver, the task of detector was to decide which of signals was transmitted. That's why we will require their detector, and the decision is to be made in the presence of noise and distortion caused by a channel. So here if you see, we can consider the following model for the digital transmission system. Here a message source transmit one symbol every t seconds, and here if you see, our symbols belong to alphabet M1, M2 up to MM. So here we are using the digital communication, so our data will be in the binary form, so that symbols are zeros and ones. So if we are taking here quaternary PCMs, we can take the symbols as 00, 01, 10, 11. It means what? From 0 to 3. So when we are transmitting the symbol at that time at the transmitter side, symbol generation is probabilistic. It means what? Here we are having the probability. We are having the different channels, different symbols, but out of which we are supposed to send. So here symbol generation is probabilistic with a prior probabilities P1, P2 up to Pm, or we can say symbols are equally likely. So if we are saying the symbols are equally likely, we can take the probability that symbol M will be emitted, will be sent. So we can take its probability as P of M of I. So we can calculate that as 1 upon M, because we are having the number of symbols, these are nothing but M. So we can take its probability 1 by M when we are taking I equal to from 1 to M. So here transmitter takes the symbol out of Mi, it will take the symbol and it will encodes it into a distinct signals. So the signal Si of t, the distinct signal, occupies the whole slot allotted to the symbol Mi. So here we can say Si of t is a real valued energy signal, and we can calculate it as E of I, that will be equal to integration from 0 to t Si square of t dt, where I is equal to 1 to up to m. So we can say the transmitter will take the symbol from Mi and it will send that to encode into a distinct signal. So here we can see what the channel will assume. When transmitter will send 1 out of Mi signal, at that time channel assumptions will be like linear. It means what? If it is saying wide enough to accommodate the signal with no or negligible distortion. It means what? When we are transmitting the data, at that time we will not require any disturbance. So we can say channel will assume that transmission will be linear. It means what? There will be negligible distortion. And channel noise is WT, is zero mean wide Gaussian noise process, and we are saying wide Gaussian noise as nothing but WGN. So we can say average wide Gaussian noise, AWGN. So we can say there is a WT is zero mean wide Gaussian noise, and there is a received signal may be expressed as it will be. We are saying that signal as x of t. So we can take x of t equal to Si of t plus WT. WT is nothing but it is the white noise, and the signal which we are sending with no distortion, we are saying that as a Si of t. So we can take x of t equal to Si of t plus WT. So here when we are sending the data, at that time channel will assume there will be no disturbance or the negligible disturbance, and here we will get the zero mean wide Gaussian noise. So receiver side, now we will see what will happen at the receiver side, which we are supposed to study in our 4th unit, that is the baseband receiver. So here receiver will observe the received signal for duration of time. We are taking the duration as t. So it will observe that for duration of time t seconds, and it will make an estimate of the transmitted signal. Estimate is nothing but it will probable, means it will assume. So it will make an estimate of transmitted signal, and it will say like process is statistical. So as a process is statistical, there will be presence of noise, there is a presence of error. So receiver has to be designed for minimizing this error. So what he will do? The receiver has to be designed like it will minimize averaging probability of that error. So here we can take P of E, that equal to summation I equal to 1 to m, because we are taking m number of symbols. So we can take here P of E equal to summation I equal to 1 to m Pi P of m cap, that is not equal to mi upon mi. So mi is nothing but symbol sent. And here we are saying it is the conditional probability which will given ith symbol was sent, because we are taking P of I. So here we can say when we are studying about the baseband receiver, there is a geometric representation of signal, and then we will consider the model of digital communication system. At that time we can say transmitter will send m symbols of duration t seconds. So here we are taking the symbols m1 up to mm. So here we can say we are sending the quaternary signals. So it will have value 00 up to 1 1 means 0 to 3. So we can say the vector transmitter will produces vector of real number. So we can take Si equal to, in matrix in column you can write Si1, Si2 up to Sin, because here we are taking I is equal to 1 to up to m. But if you see, n's value will be less than equal to m. So we can say here the modulator construct the signal Si of t for duration t seconds, and you will get the energy of signal, that Ei of t. You can see here the energy of signal you will get as integration 0 to t Si square t dt, where I is equal to 1 to 2 up to m. And when transmitter will send, at that time channel will assume two characteristics. It means what? It will assume it is a linear with bandwidth that is large enough to accommodate the transmission of the modulator output without distortion. It means what? Channel can assume there is a zero or a negligible distortion. So the transmission is linear. And again there is the transmitted signal. Which the signal we are transmitting? Si of t. So we can say the transmitted signal Si of t is affected by additive, zero mean stationary, white Gaussian noise, which we are denoting by Wt. So here you will get zero mean stationary, white Gaussian noise process. And the channel is known as additive white Gaussian noise. AWGN is nothing but additive white Gaussian noise. So we can say you will get the received signal, that is, you can take x of t, you can take s of t, that is nothing but the signal which you will get at the receiver. So the received random process is Si of t plus the white Gaussian noise. It is nothing but additive white. So you can take Wt. So we can say Si of t plus a Wt. So you will get that signal at the receiver side. So here now we can see about the geometric representation of signal. So if we are sending here the set of m energy signals, that is, we are considering as a linear combination of n orthogonal basis functions, where we are taking n is less than equal to m. So we can say to represent any set of m energy signals, we are sending from 1 to m energy signals. So we are taking Si of t, I equal to 1 to m, as a linear combination of n orthogonal basis functions where n is less than equal to m. So to do that objective, we can take our energy signal S1 of t, S2 of t, S3 of t up to Sm of t. Each of duration we are taking as a t second. So you will get, how we will get? We have seen that we will get energy signal Si of t, that is equal to summation I equal to 1 to m in summation I equal to 1 to n Sij phi j of t. So we can say Sij, that is the coefficient, and phi j of t, that is nothing but orthogonal basis functions. So you will get Si of t as a summation I equal to 1 to n Sij phi j of t. So here we can say you will get the coefficient you can take as Si of j, that is equal to integration 0 to t Si of t phi j of t dt. So here we can say So here we can say that as a Gram-Schmidt organization. So the Gram-Schmidt organization states that when we are taking set of m energy signals and we are taking m value is greater than equal to n. So here we can say we will get the signal SIFT that can be expressed as linear combination of n orthogonal functions. So you will get SIFT that is equal to, you can take that and you can say you will get the coefficient as Si of j that is equal to integration 0 to t Si of t phi j of t dt, where I value is 1 up to m and j value is 1 2 up to n. Here by mistake they have written m, but you will require for j 1 2 up to n, because here we are taking ij. So I value is from up to m and j value is from 1 to up to n, because we are saying m value is greater than or less than n. So here you will get the real valued functions. So we can say the phi j of t are the basis functions, orthogonal basis functions, and Sij are the scalar coefficient. Phi j is the orthogonal basis and Sij is the scalar coefficients. So we will consider the real valued functions phi j of t which are orthogonal to each other. So you can take orthogonal to each other, so we can say real valued basis functions, and you can take integrations 0 to t phi I of t phi j of t dt equal to del ij, that equal to 1 if I equal to j, and that equal to 0 if I is not equal to 0. So here we can say each basis functions had unit energy over the symbol durations t. So if we are taking the basis functions are known and scalars are also given, we can generate the energy signals. So we can generate energy signal, we will see in the following diagram. So we can say here the set of coefficients can be viewed as n dimensional vector and it will denoted by Si, and it will bears a one-to-one relationship with the transmitted signal Si of t. So here we can see the waveform, the diagrams, sorry, not a waveform, the diagrams. So we can say here the pictorial depiction of our equations. Which equations? Our equations which we will get as a Si of j, that is equal to Si of j we will get equal to integration 0 to t Si of t phi j of t. And again if you see the first diagram, here we are saying it is the pictorial description. So we can say that as a this diagram is nothing but it is the synthesizer for generating the signal Sj of t, and diagram B is the analyzer for generating the signal vector Sj. So here we are taking the signal in the set Si of t, it is completely determined by the vector of its coefficients. So here we are taking I equal to 1 2 up to m. So we can take the signal vector Si that can be extended to 2D, 3D up to n dimensional Euclid space, and it will provide the mathematical basis for geometric representation of energy signal that is used in the noise analysis. So it will allow the definitions of length of vectors, angles between vectors, squared values, and you will get modulus, double modulus of Si square, that is equal to Si raised to t, it is nothing but the matrix transposition into Si. So you can take that as summation I equal to 1 up to n Si j square, where we are taking I equal to 1 2 up to m and j equal to 1 2 up to n. So here we can say when we are taking the signal set Sij of t, we can say that will derive a subset of linearly independent energy signal. Sij of t, where I equal to 1 to up to m and j equal to 1 to up to n, where n is less than m. So we can say when we are finding the energy of S1 of t, as this energy it helps in the first basis functions, that is nothing but first basis phi1 of t, which is normalized form of the first signal. If we are supposed to find the second scalar S21, energy of second signal, a special function g2 of t, which is orthogonal to first basis functions, then we will get the second orthogonal basis function, that is the phi2 of t. So we can follow that same procedure finding the second basis to obtain the other functions. So here we have seen about the geometric representation of signal and the Gram-Schmidt organization.